Hi, everybody. Good to see you. I mean, I can't really see you, but I wanted to do this little mini lesson for you. I'm still in the hospital, as you can see. It's 10:10 p.m. on Tuesday night, so no baby yet, but we expect the baby to be born hopefully by Thursday. So I won't be here Thursday like I initially thought. I will be back Friday. We have a lab that we're doing on Friday. Mr. Ekman's class is doing the lab today. By today, I mean Wednesday. With his students, we'll be doing it on Friday when I get back. So be good to your substitute, please. I know you guys will do really well. I wanted to take this time and talk about gravity and what gravity is. We've defined it before. It's a force of attraction between any two objects. There was the clearly thought out statement of you have an attractive force to the person next to you. While true gravitationally, the more massive an object, the stronger that gravitational pull is. That makes sense when we take our formula for the force of gravity. Force of gravity is equal to mass times the acceleration of gravity. If I increase the mass, the force increases. But the issue with that equation as it stands by itself is that it only works on Earth. I can only find the force of gravity on Earth of an object. That is what that equation allows us. Incredibly useful. We live on Earth. That's pretty much all we're going to deal with. So it is incredibly useful. But when we're dealing with planetary motion or celestial bodies, that's when it gets a little more complicated, because I cannot use the acceleration of gravity in that context. I need to use something else. I'm not going to derive what we're doing for you. I'm just going to give you the information. If you have questions, you can always email me. There's a CK12 on this, so you can read the CK12 if you want. But let's jump into it. This is our scenario. We have two masses, M1, M2, and they each have a force that's pulling on the other. Those forces are equal to each other. Just like how the force of gravity that the Earth is putting on me is equal to the force that I put on the Earth, because they cancel each other out because we're touching. So you have those two forces, those two masses, and you have a radius r. When I'm measuring r, it's from the center of one mass to the center of the other. If I were to measure the radius r between me and the Earth, it would be the center of the Earth to my center of gravity, or my center of mass. So that's how that's measured. When we talk about the equation, it looks like this. We have a big capital G, and then we have the two masses multiplied together divided by that distance, that r squared, that radius distance. That G, that's called the universal gravitational constant. It's only one number. It does have units, so it's not a coefficient like mu in friction. That is the value. It's 6.7 times 10 to the negative 11 Newton meters squared divided by mass squared. You can see how that's kind of derived if you were to put those units in with mass and with that distance squared and see what that balances out to. You would get newtons by multiplying the constant times the two masses and divided by the square of that distance. But this is what it looks like. What I want you to ponder, how does the force of gravity change as mass increases? If I were to increase the mass of one object, or both objects, as long as one of the mass increases, because I'm not changing the distance, and G, capital G, is a universal constant, so it will never change its number, the force of gravity increases as the mass increases. So there's a huge force of gravity that the Earth has on whatever mass is around it because it is so massive. Hence, it has a large gravitational force. Here they are a little bit more close up, so you can see them. Write these down in your notes. Familiarize yourself with them. If you need to pause this video so you can write this down, please do. because we will be seeing this on the test a week from today being Wednesday. That is pretty much it. There's a CK12 practice which shouldn't take you very long. You should have already completed the centripetal motion CK12. I don't think that there's a practice that'll upload, but your substitute will know. I know I'm rambling. I'm tired, but that's pretty much the mini lesson. I hope you have a great day. Please make sure you get that CK12 done and be productive today. You're rocking at the hospital with Mr. Graham.